Biomolecular dynamics and function, and before that I like to thank the organizers of this conference, particularly Ross and Dan, for their kind invitation. So I'm from SNBO Center, that I say. So that is the biomolecular dynamics. So before going to that main topic, that is the hydration dynamics particularly, let me give you the brief overview of the dynamics in a real biomolecules. Like it could be the hydration dynamics, whatever I have mentioned previously, like the dynamics of the water molecules in a closed vicinity of either protein or the DNA, or it could be interfacial dynamics, like when a DNA recognizes one protein. So interface makes plays a very good role to make the complex, because sometimes the protein has to be detached from the DNA, something like that. Or it could be the energy transfer that many speakers over here mentioned, energy transfer, like from the light harvesting process, and also the electron transfer in the protein, because some of the electron transfer proteins like cytochrome C is very, very important, very, very important protein. So my main question, whatever, is it okay? Yeah. Okay. So my main question is, I already mentioned, to find out a correlation between function and the dynamics. Particularly function means I'll focus on the hydration dynamics particularly, and it is important to maintain the structural integrity, because if I want to find out a correlation between function and the dynamics, I have to maintain the structural integrity. That is important, extremely important. So we are careful about that. So when we talk about this hydration dynamics, we want to talk about the water. Like, water is really important for our life, and lots of effort of NASA is going right now to find out water molecules in Mars, because they thought here, there is some statement, I don't know if it's visible from your statement, that if they can find out the water in Mars, they can find out the existence of life in Mars. Yesterday night I was talking with Ross, and his father also believed that dry protein is a dead protein. So no water, no life kind of stuff. So if we consider the history of life in our planet, we will find a very interesting stuff over here. So if you consider that this axis is the time axis, and this is the events that is going on in our planet, you will find that after the cosmological events, water came in our Earth. And then small molecule to complicated molecule, fishes, dinosaurs, and this is the human civilization. So this is very, very small in the evolution pathway. So life had to spend lots of time on the top of water to come to the land. So that was probably a trade-off between life and water. Water allowed life to go to land, and life took it as an essential part. So something. The real origin of life experiment came from Professor Miller in early 1950s. He showed that using this methane, ammonia, hydrogen, and water vapor, if you just use the electrical flash, then after 30 days or something like that, they found a small protein, an amino acid, glycine. So he proved that how water is important for the formation of the amino acid. So these water, we can define that this is cosmological water. And if you think that water molecules in a close vicinity of the protein and the DNA, so these are also important. Take a polypeptide chain and throw it in a bucket of water, then it will fold like that. So that in the protein folding, hydrophobic amino acid will try to hide from water, and hydrophilic will be exposed to this water, and this particular shape of the protein will be formed in water. So if you have a closer look in the close vicinity of a protein, you will find the water molecules are ordered, not ordered like that, this is the cartoon, and compared to the tetrahedron model of water molecules in dark water. So, but if you have, little bit more imaginary, you will find that there is two kinds of potential over there in the protein surface. So this is the bound water, and that is the free water. So there is always dynamical exchange between bound water and free water. And that is important. So over here, in a very, very simple model, but it is not too simple. So in a simple model, we say, we relate the residence time of water molecules at the protein surface with the solvation time of the water molecules. So we define this water to be biological water. So it is not a simple problem, let me tell you. Of course, it is not simple. So big brain had to assemble together to find out some answer on that. So it is a very, very old story, and I can give another 20 minutes talk on that, the history of hydration. So consider the Max Pedus. Here in 1962, he found the water molecules in a crystal structure of hemoglobin. And after that, another Nobel laureate, Kutris, found that the dynamical nature of the water molecules by using NMR. And recently, Professor Zuel, actually we first time got what is the exact time scale of the water molecules at the surface of the proteins. So, but to get the dynamical nature of the water molecule, this is also very old story. In early 1957, Grant did a very good experiment, dielectric relaxation experiment. And in the dielectric relaxation experiment, you will find in a bulk water, in the imaginary component of dielectric constant, it is giving only 1 tick. And if you convert it to time, it will give you about 10 picosecond. But in protein solution, is a lysozyme myoglobin solution, you will find lots of peaks, at least 3 peaks. So one corresponds to 10 picosecond, another is 80 picosecond over here, and several microsecond. So he defined that thing, that 80 picosecond, whatever you found from dielectric relaxation experiment, that is the bound type of water molecules. So let me tell you what is the physics of measurement of hydration dynamics in our case particularly. And thanks to Dongping already introduced these figures to this audience. Like what we did, we took a chromophore which could be covalently attached or very, very deep or here at the surface of the protein over there. This is the chromophore and this is the water molecules. So we create a dipole moment in a femtosecond time scale over there, which is represented by an arrow, and then the water molecules in a close vicinity of that chromophore will try to reorient themselves around the instantaneously created dipole moment. So that state is a higher energy state, and then it will try to come to this equilibrium state. So if you consider a full spectrum, this end will give you high energy side, and this end will give you low energy side. Consider that this is the blue end and this is the red end. And as a consequence, what you will get in a time resolved spectra, that you will get the decay in the blue end, because all the population is going for the equilibrium, and rise time in the red end. So that is the signature of this kind of solvation. And this is the simple, like simpler than mean, like whatever he described. That this is a simple pump, optical conversion setup that we had at Caltech to measure this hydration dynamics. So what was our observable? Here is our observable. So if you take a look of the decay, you will find the decay in the blue end and rise in the red end. So that is the signature. And then you can, by using 15 decays or 20 decays, you can really construct time-resolved emission spectrum. So this is the time-resolved emission spectrum. And as you may find, the peak of the time-resolved emission spectrum will go. So this is the 0 picosecond, and eventually in 12 picosecond, it goes over there. Now, if you take the peak and then put in a formula called nu of t minus nu of infinity divided by nu 0 minus nu infinity, that is the normalized function called solvation correlation function or hydration correlation function, that will give you a decay of that. So by numerical fitting of this decay, you will know that how fast or how slow are water molecules relaxing around the instantaneously created dipole moment of the chromophore. And believe me, this is a very, 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 very sensitive technique. Like, consider that decay, what Ross already showed, the decay in the water molecules, it is about 1 picosecond. Of course, due to our limited resolution, we couldn't resolve time constant below 100 femtosecond. What Professor Fleming gave idea that huge component will come from this inertial motion of the water molecules. That would be about 100 femtosecond. So it is 1 picosecond, and if you add 6 molar of guanidine hydrochloride, which is the potential denaturant of protein and DNA molecule, decay will become much, much slower. So this is really very, very sensitive technique. Now we went to a protein called substilicin Carlsberg, and it is a single tryptophan protein. So tryptophan is sitting at the surface of the protein over here, at the surface, and then what it is giving, that we followed the same methodology, like time-resolved emission spectral technique, and we recovered that time scale over here. One is 1 picosecond, that is the bulk type of water, and we found the 40 picosecond, that is the slow signature of the slow water. So we found the signature of this biological water in the close vicinity of protein molecule. Now we wanted to explore the extent, like how long they are extended at the surface. So it is like very, very thick or thin. So to do this experiment, what we did, we put a chromophore, that is the artificial covalent bonding of that, which is about 7 angstrom away from the surface of the protein. And what we found over here is nothing, like less is known. So it is already bark-like, so 10%, 20% rigid water. So most of them are like bark-type water. So this experiment is telling that the biological water is existing at the surface of the protein, but it is not much thick. Okay, now we want to think from a different corner, the thinking function of biomolecules from the corner of dynamics. So I showed this slide previously, and this is our motivation, like whether we can predict the biological functionality by using ultra-fast dynamics, like hydrogen dynamics. So we work on a protein which is a sweet, as I told you, and it is 50,000 times sweeter than normal sugar. So this is the protein. So it is very, very attractive to diabetic patient that you are not consuming sucrose, only taking protein, but it's fat. But if you denature it, that functionality will go and it will become bitter. So we found the signature of that this is the denatured protein. So lots of slower dynamics is contributing. That is essentially coming from the polar residues of the protein. But in a native state of the protein, it is giving 1 picosecond and about 20 picosecond. We worked on another protein, and here the protein, the probe is artificially attached over there, but we are lucky to have a crystal structure of that protein ligand complex. So the ligand is ANS, that is a dye. And it was found by biochemists for a long time that this protein alpha-chymotrypsin was generated in a close vicinity of a duodenum, that is our stomach, where the pH is 3.7, but it is not active over there. So it had to traverse a long path to lower intestinal tract to be activated, where the pH is 7. So, and there was lots of theory. Everybody said that it is the protonation of the histidine side, that's why it is not active. So we wanted to get more idea about that. That is there any role of the solvation dynamics or hydration dynamics over there if we change the pH? And we found it is. So when the protein is active at the normal pH, like pH 6.7, then hydration dynamics is pretty fast. But whenever it is non-functional, like in pH is pH 3.6, then it is, you see, that the dynamics is much slower. So it is like salesman attitude of the water molecules. When the shop is no customer is there, then salesmen are very, very active to find out the customer. But whenever customer is there, then they are silent, like they are very, very slow. So you will find over there. So that kind of activity that we found. Not only that, this protein, we did again the substilicin Carlsberg, but we control the activity by using a different solvents. Like if you use the acetonitrile, dioxin in different mixture, then if crystal structure said that the structural integrity will be retained over there. And this is the way we measure the structure, functionality. Like we have a probe, like a substrate, that will give absorption over there, but when it is in a product form, it will give this absorption over there. Now, if you have an eye over here with time, you will find that in a bulk water, that product formation rate is very, very high. But if you add little bit acetonitrile or the dioxin, within the structural integrity of the protein, that thing will go down, like 60 times, 100 times down over there. So we found a very good correlation of this hydration dynamics, that what is going on in the hydration dynamics over there in the close vicinity of the tryptophan and the functionality. We again found that when the protein is not functional, the dynamics is slower. That is evident over there. So we worked on another protein. It is a membrane-bound protein, and it is bovine phospholipase. And the real activity is over here. So in a free form, it will first bind to a membrane and then look for a substrate which will be hidden over here, and then find out the substrate and then eat it. So to mimic this thing, whatever we have done, we took a micelle. Micelle is a mimic of a membrane. And we took this thing, and then we tried to get idea what is going on after complexation of the enzyme with a membrane. And we found a very good stuff. You see that when that protein didn't find the membrane, the dynamics is very, very fast. It's again 1 picosecond and 20 picosecond. But when it found the membrane, like its functionality is done, it doesn't have to fight for this membrane, then it becomes really slower. This is the anisotropy of the tryptophan, that is our probe, that will tell the physical motion, how the physical motion, what is the dynamics of the tryptophan itself, and you will find that it is not decaying. That means it is static. So the question of the self-salvation we can ignore that possibility. So in a very, very simplistic molecular dynamic simulation from our group, we're trying to get some idea. It is not like very, very high power molecular dynamics like Dongting did right now, but it is a little bit low power. And what we did, we just calculated the survival correlation function. So what is survival correlation function? Survival correlation function will essentially tell you that if you consider a radius of R and consider the number of water molecules. So if one water molecule leaves out of that radius, then you will lose that water molecule. So that's why you will define that the survival correlation function, like how long a water molecule is staying in a particular radius. So we found that in a 6 angstrom radius, close to 6 angstrom radius, that the dynamical nature of the water molecules is pretty good in agreement with our femtosecond experiment that was giving 1 picosecond and about 20 picosecond. Of course, we found some of the trajectories of the water molecules. This is the very, very long resident water molecules, and this is a short lived water molecules that was staying in a vicinity of 6 angstrom. And here it is shown in a cartoon that how the water molecules is doing. We found the same event in DNA hydration. So we took a drug is a fluorescent, and the drug is anti-helminthic drug and is a minor group binder. So this is over there, and we have a crystal structure, NMR structure, everything that the drug is bound over there. And what we found in a dodecamer DNA, that it is 1 picosecond and 20 picosecond, and anisotropy is telling that this is a short DNA, so DNA as a whole with the complex is rotating. That's why this is decaying. But consider a genomic DNA which is very, very long, that's no question of the rotation of the DNA itself. We found that anisotropy is not decaying, but the hydration correlation function is decaying with the same time scale, 1 picosecond and 20 picosecond. Okay, so that was the artificially created complex. So to convince people, what we did, we took a modified DNA. Like we took adenine out and put 2-aminopurine, which is a fluorescent analog of this of the base. And what we found again over here is 1 picosecond and 20 picoseconds. So that is again the hydration dynamics that we said. Now our question is that we found that hydration dynamics, we know the real time scale, we know that how long they are extended from the surface of a protein or the DNA, we know everything. Now our question is, can we control the biomolecular function by controlling the dynamics of hydration? That is our basic question. One route of doing this thing is called physical route, is a control of humidity. Another route is called chemical route, that is called reverse micelle and the other biomimetics. Like if you consider the reverse micelle, this is a very good system. 2 minutes? Okay. 2 minutes? I'll finish it. So it's a very good system. You can control the water molecules in the droplets over here. Outside is the alkane, and this is the small water droplets, and you can control the radius of this in angstrom resolution. And also in micelle, you can control the water molecules around that. So this is a very, very well characterized. So in a recent book chapter from our group, we really did something like we did give a brief review of what is going on in our group, like modulation of water dynamics, a novel approach to control enzyme functionality. There we mentioned that in a reverse micelle, so if you put some enzyme molecule in a reverse micelle and control the hydration by controlling the radius of the reverse micelle, you can really control its functionality. And in the micelle also, same story is valid. Like if you just make a complex within the structural integrity of the protein over there, the same stuff, you can control its functionality. So that is functionality will go down. But if you increase this the size of the reverse micelle, you can again retrieve that functionality. So, but we have to be careful about that, because if you just put these biomolecules in the reverse micelle or the micelle, then there could be other consequences, like protein folding pathway. So protein can become unfolded in a low hydration condition. And also, like we observed some beautiful stuff, that how solvation is going on in the nanospace, and that would answer one of the means question, that how we know that it is the hydration, not the solvation. Because if you keep the structure same, and if you just make the surface water molecule less labile, you will get a longer time scale. So that thing was addressed in that paper. And also we did the DNA, and we found in the nanospace, the ligand binding property of a DNA is completely different. It is not like simple in vitro system. So the most of the work that I have done with Professor Zuel at Caltech, and I should acknowledge Professor Zuel and Caltech group, including my senior colleague, Don Ping Tong. And we are also doing something in India right now to control. So these are my students, postdoc Rajiv, and they are the senior student. They are right tradition, and we have a collaboration with Professor Morgan at Durham University, and funding Department of Science and Technology. And thank you very much for your kind attention.
Thank you, Samir. Thank you for being on time. So we've got room for a couple of questions now.
Okay. I'm really sorry to ask you this, but could you please show me the slide on chymotrypsin experiment, alpha chymotrypsin, pH-dependent experiment?
Yeah, oh, sure.
Sorry. But anyway, I just asked a question.
Yes.
When you did that experiment, you were still probing tryptophan.
No, ANS.
ANS.
Yeah, it's a very good question. Yeah, ANS is sitting over there.
Does that contain any amine, secondary or primary amine?
No, actually, there is a 1,122 disulfide bond, and it was clearly explored in the X-ray structure that the ANS will be sitting over there. So its binding site is completely different from its enzymatic active catalytic site.
That ANS compound does not have any
Exactly.
chemical group that is sensitive to pH.
No. And it is far away, exactly diametrically opposite point of the catalytic center. It's a very good question. Otherwise, you would say that it is perturbing that enzymatic activity. Yeah? Yes, sure.
I have difficulty believing that this is really related to water dynamics as opposed to also just fluctuations within the process, especially when you're adding things like denaturing agents.
Sure.
Part of the reason why I would say that is that when we've looked before, this was some time ago, trying to reproduce the data from Butrix, for example, which I did do personally for water lifetime, you find that there are some waters which are very specific, but what you don't find, or what we could never find, is a general ordering. You may find a lower exchange, but whether this is really a property of the small fluctuations or whatever it is in the protein, as opposed to just the fact that I have a wall or a shape in the water which is slowing down my local dynamics. Because the ones that we did find were different were tended to be buried in crests or in what. So how can you make the separation when you add the nature and say this is really the water and it's not really some...
Yeah, exactly. That was the specific question that me asked also that day to Godfrey. Like, first of all, that it is not like one protein that we are talking about. We took at least 5-6 proteins, and thing is that is everything is giving the tryptophan, for example, but tryptophan is sitting in a different position. But the condition is everybody was sitting at the surface of the protein. So that is the criteria. So this is the surface protein. We are not talking about the cavity or premix kind of stuff.
No,
this is number one.
I mean, just putting in because when we were looking once at a one-surfactant protein, I mean, one of the arguments was, which will come again, the water ordering that we saw was exactly the same ordering as what you'd see against any surface.
Yeah.
Okay. I mean, you're just getting a surface effect. It's not really a functional protein effect. It's just that I have a surface, and in which case that you get some degree of ordering in your first layer, which is of course different to bulk. And what I'm worried is that what you're seeing is a reflection of this, and not really a reflection of a functional change or something which is really related to the fine dynamics of the protein in the different environment. Not that the effect isn't real. I mean, the effect is of course real, and that there is slowing of the water molecules around the protein.
Right.
But the question is, can you relate it to these functions?
That we are trying right now, because artificially again we are controlling the water molecules at the surface of the protein and the DNA, and we are trying to find out that whether we can retrieve to the bulk limit or not by using some biomimetics. That is the exact question that we are trying to find out. For example, the pH study, somebody will argue that in the low pH, the active site will be protonated. So whether it's a slowing down of the water molecules has some consequence to that functionality or not, that is a question. We say,
some changes in the
right. So it is something, but that's why we are exactly focusing on that problem. That if we control the water molecules, only water molecules specifically, can we control the functionality?
Can you get some information by using D2O or to try and differentiate these things? Would that give you any
deuterionic
deuterated water, D2O, heavy water.
Deuterated water. Actually, you are right that here in this protein we did that experiment, and also in the modeling we have done this thing, and we found that there is 1.5 to 1.8 times change in solvation dynamics. It is becoming slower, but there was a very good theory from Professor Bakchi, India, and they predicted that if you just consider the solvation dynamics of a probe in a deuterated water, you will get at most 50%, not more than that. So, because the rotational kind of stuff will contribute more over there, and we exactly found over there.
Last question, I think, Professor Hush.
Actually, this is from left field, as you might say, that we're talking about chemistry. I wonder, is it known that the kinetics of exchange from
It's a dynamic
down
amount of
and say the mixture molecules have been measured for a long time in chemistry. If you have, for example, a nickel ion in water, the first shell of water molecules forms a very well-defined regular octahedron, so very well ordered. Then you might say that the next water molecules will be somewhat loosely connected. And it was shown by Henry Tarby, a long time ago, using isotopic exchange, so that you could actually measure the exchange of the outermost and the innermost, and so you measure the rates. These are on the NMR. And then, of course, you can measure there are two possible mechanisms, which in chemistry are called SN1 and SN2, which I'm sure you can defend later what that means. But it means that it either operates in a cooperative kind of way, or else it operates in a way in which one molecule comes down and one molecule. These will have different pressure dependencies. And a lot of work going on for many years to distinguish but the answer is that both have different systems. But so that's isotopic exchange. And so these rates are well known, and I wonder if that could be possibly have any interest in coding.
Actually, we try to do this kind of stuff in a simplistic model, like here. Here in this work, we attempted to do this kind of stuff.
Yeah.
This is a simplistic model. That how this convection dynamics is related to the residence time, like the exchange time of the particular stuff. So considering the Onsager continuum and everything.
In the case of the nickel simple right? So
productive was
very
also
simple.
in a very, very simple one.
Okay, I think we'll finish there, and we'll thank all the speakers for the session and coffee.
Before you run off for morning tea, I just wanted to check a few practical things.